I'm Lauren Hoffman, and I will be talking about Maxwell-Boltzmann distribution. So, up to this point in our discussion of gases and their properties, we have only considered the average values for all molecules to be the values for the gas. So, for example, we've considered the velocity of a gas to be the average velocity of all the molecules in the gas. But in reality, we have to take into account that a distribution of speeds and energies exists among molecules, so not all molecules travel at that same average velocity. Some of them travel faster and some of them travel slower. So we've generalized so far that a speed of a molecule increases with the temperature. We can see this in hot coffee, for example. You'll notice that it kind of condensates on the lid. So the main phase of the molecules in coffee is liquid, but since it's hot, a few of these have large enough speeds and temperatures to escape into the gas phase, which creates the steam, which then condensates onto your sides of your coffee. So this explains why that happens. So at a given time, the number of molecules possessing a certain heuristic, such as energy, can be expressed by this thing called number density. This is what Boltzmann created. So it kind of has to follow the property that the number of molecules having energies ranging from E to E plus delta E is equal to the number density times a change in energy. So we kind of know that molecules and atoms can only occupy certain levels of energy, and so this Boltzmann's distribution of energy shows the probability of finding a molecule in a particular energy level. So the equation says that the probability of finding a molecule varies exponentially as negative E over Boltzmann's constant times temperature. So that was kind of used to describe how molecules, the different energy states of molecules, but Boltzmann wanted to go further. He wanted to be able to describe their speeds and speeds of different molecules at different times. So he derived this equation, and it describes the distribution of speeds of gas molecules at varying temperatures. And so when you make a graph of the velocity versus the number density of the molecules and you integrate it, so take the area under the curve, that is equal to the total number of molecules with the speed in that given range. So from this, we can see that, looking at the graphs, we can see that as the temperature increases, the area under each of the graphs becomes greater, so more molecules have a higher speed. From Boltzmann's equation, you can see that if you, at a constant velocity, as you increase the temperature, the number of molecules with the fixed velocity, so the number density, will increase if you have a decreasing mass, and it will decrease if you have an increasing mass, and this happens due to this little exponent here in E. So there's kind of three types of velocity we can describe under this law. So there's the root mean square velocity, which is the square root of the average velocity squared. There's the average velocity, and there's the most probable velocity. So this graph, you can kind of see where each of those lie. You see that the most probable velocity is at the peak of the graph, and this is the with the highest ratio of molecules. So you're more likely to find a molecule with that speed at that velocity. So the average velocity is just the average of the velocities, and you can see that these three are related by relating them to temperature, Boltzmann's constant, and mass of the molecule. And also, the root mean square velocity is always greater than the average velocity, which is greater than the most probable velocity. Jungle Boy, Jungle Boy. So why does evaporation feel cold? So you'll notice when you jump into a pool on a hot day and then come back out, you're a little wet and you start to feel a little cold when the water starts to dry off. This happens because some of the molecules that are in the liquid are moving faster than others, especially as the surrounding heat and the air gives them energy to escape. So as they move faster and faster, they escape from the liquid into a gas by evaporation. And the molecules that are left behind then have a lower kinetic energy and therefore a lower temperature. So this is why it feels cold. This is also why Gucci's bling is so cold, because metals have lots of electrons moving around, so with high velocities. So with these they're conducting, and so when they move at this high velocity, they need energy from their surroundings, so they take heat, and so they feel cold. So we have a little problem here. At what temperature would the average speed of helium be equal to the escape velocity of the moon? And B, what are VRMS and V most probable at this temperature? So we're given the mass of helium is 6.64 times 10 to the negative 22nd kilograms. That's the mass of a molecule of helium. And the escape velocity of the moon is 2.37 times 10 to the third meters per second. Using equation B, we say that escape velocity of the moon is equal to average velocity, which is equal to 1.6 times the square root of Boltzmann's constant, which is a given, times temperature, which we're solving for, over mass, which is the mass of helium. Solving for temperature, we get that T equals 1.06 times 10 to the third Kelvin. So at this temperature, helium atom could escape velocity of the moon. Solving for part B, we plug in T for equations A and C, getting the root mean square velocity is 2.57 times 10 to the third meters per second, and the most probable velocity is 2.09 times 10 to the third meters per second. In comparing these three, we find that, yes, it is true that root mean square velocity is greater than average velocity, which is greater than most probable velocity.